If you want to solve complex problems in science and engineering today, we assume you need to start right here. You spend 4 to 8 years sitting in a lecture hall, passing exams, and earning an elite degree before you're allowed to touch the real work. Yet, if we look back at the architects of our modern reality, the people who actually built the technologies we rely on, they routinely failed to meet that requirement. The modern alternating current power system, the grid that electrifies the globe, was engineered by Nikola Tesla, a college dropout. The personal computer sitting on your desk stems from designs by Steve Wozniak, who did not hold a degree when he built the Apple I. And the first successful, controlled, powered human flight was accomplished by two brothers who never even attended college. These individuals consistently bypassed highly educated experts to solve the hardest problems of their eras. We have to ask how their complete lack of formal training actually worked to their advantage. In the 18th century, the British Empire faced a massive navigational crisis. Sailors could not accurately calculate their longitude at sea. The academic consensus, backed by scientific giants like Isaac Newton, insisted the answer lay in complex astronomical observations. They spent years staring at the stars, trying to calculate their way out of the problem. John Harrison was an English carpenter and self-taught clockmaker. He completely ignored the celestial theories coming out of the Royal Academies. This is the marine chronometer Harrison built. Instead of relying on the sky, he engineered a hyper-precise physical clock. By utilizing specialized metals and a gimbal system, this mechanical object maintained accurate time even during extreme temperature shifts and the violent rocking of a ship. While the academic establishment spent decades trapped in rigid astronomical theory, a self-taught carpenter solved the problem by manipulating tangible, physical reality. Curious, this raises a practical question. Without professors or a structured syllabus, how do these individuals acquire the high-level knowledge necessary to invent these machines? Michael Faraday acquired his foundational physics knowledge by working as a bookbinder's apprentice. He simply read the scientific texts that customers brought into his shop to be bound, giving him the education that eventually led to his discovery of electromagnetic induction. James Buchanan Eads approached civil engineering the exact same way. Having no formal schooling beyond his youth, he taught himself the principles of mechanics entirely by reading books stashed in the library of a dry goods store where he worked. This postcard captures the Eads Bridge in St. Louis. Eads leveraged his self-taught knowledge to engineer these massive structures, successfully designing the very first major bridge built entirely of steel. A forced curriculum often creates friction by pushing students through standardized paces. When a learner is driven entirely by their own organic curiosity, that friction disappears, resulting in obsessive, highly specialized expertise. That specialized expertise directly fueled their physical experiments. In the race to achieve human flight, academically trained scientists were busy publishing theoretical papers on aerodynamics. The Wright brothers, meanwhile, were physically building their own wind tunnels to test actual wing shapes. This photograph shows the Wright Flyer suspended over the sand. They solved the incredibly complex physical problem of flight control, not with abstract math, but by applying the hands-on mechanical skills they learned from building bicycles and printing presses. We see the same pattern during the Industrial Revolution. While academics studied thermodynamics on paper, James Watt, a mathematical instrument maker, spent his time physically taking apart a broken Newcomen steam engine to see why it was so inefficient. Through hands-on analysis, Watt realized he could pull the steam into a separate cylinder to cool it. This kept the main cylinder continuously hot, which drastically reduced fuel consumption and created the power source that drove the global railway boom. An autodidact's primary tool is relentless physical trial and error. By operating directly in the real-world sandbox, they can test and iterate faster than anyone working out theories on a whiteboard. As technology became highly complex in the 20th century, you might expect this individual outsider advantage to vanish. Instead, it scaled, allowing single individuals to outpace heavily funded corporate engineering teams. Philo Farnsworth conceived the first fully functional, all-electronic television system while he was still a high school student in Idaho. He bypassed the clunky, mechanical television prototypes that massive corporate engineering departments were struggling to perfect. Looking closely at this circuit board highlights the kind of elegant hardware design Steve Wozniak achieved. Relying purely on self-directed study, he engineered software and hardware systems that were far more efficient than anything his credentialed peers were producing. Uncredentialed minds don't carry the baggage of institutional inertia. Because they aren't trained in the accepted standard methods of their fields, they are free to leapfrog established industries entirely. A formal university education is an incredibly valuable tool, but history consistently demonstrates it is not the exclusive gatekeeper of competency. The defining trait connecting these innovators is not a framed diploma. It is an innate mindset of intense curiosity and a stubborn willingness to tinker in the real world until a machine works. Historical autodidacts achieved their breakthroughs despite severe limitations. They relied on local bookshops and dry goods store libraries to patch together an education. Today, we have instant, unlimited digital access to the entirety of human knowledge. The modern era provides every piece of raw information you could ever need. The only prerequisite left is the curiosity to start building.